Alright, problem 5b, same idea as 5a. We need to take this fraction, and if you think about it, since we're doing a summation, well, I don't care what value you plug in, what n value you plug in, we're always going to get a positive fraction. So we're just going to get a series of positive fractions adding together if we just start to list terms, and that's not going to help us. So we want to write this as a partial fraction, because then hopefully one of those fractions will be negative, and we'll get some things that cancel out nicely. So let's do that. Just like the other examples we've done, start by factoring that denominator. So n squared plus 2n, we can factor an n out of both of those terms, and we're left with n plus 2. And now we want to split this up into two fractions, one with the denominator n and one with the denominator n plus 2. Cool, cool, cool. Good start. Now we need to multiply by the denominator on both sides of this equation. So if we do that, on the left, we will be left with our numerator, 4. And on the right, if you think about multiplying by the denominator to that first fraction, those n's are going to cancel each other out, and we're going to be left with a over n plus 2. Plus b over, same idea, except this time the n plus 2's are going to cancel out, so we'll be left with plus b. Oh, okay. Alright, problem number 5b. Just like 5a, we have some series here, an infinite series. We're trying to find the sum of it. It's not geometric, it's not arithmetic, so we don't know how to do it. We could start listing terms out, consecutive terms, but notice if we do that as it is right now, we're putting positive numbers into n squared plus 2n. Every single fraction we get would be a positive fraction, so nothing would cancel out, nothing interesting would happen, to my knowledge. So that doesn't really seem like it's going to help us much. But maybe if we can take that fraction, 4 over n squared plus 2n, and write it as a partial fraction decomposition, well, maybe one of the fractions that we get might have a negative coefficient, and then maybe some things would cancel out in an interesting way, and we could find a pattern of terms canceling each other out, and we might actually be able to find this infinite sum without knowing a formula for it, which is really cool. And again, this is called a telescoping series, because if you can imagine like a compact telescope, you can like pop it out and it'll turn into a long telescope. Like same idea with those Star Wars lightsabers that you can get at like Target and Walmart that little kids play with. Like if you like poke someone with it, it collapses into itself. It's like the same idea here. So that's our goal. So remember, to do that, the first thing we want to do is we want to factor the denominator as completely as possible. So in this case, if we factor our denominator, we're going to get 4 over, and we can factor an n out of there to get 4 over n times, well, what's left? We're left with n plus 2. And then check yourself, n times n is n squared, n times 2 is 2n, so we're good. Okay, well that's step 1, and once we do that, we want to then rewrite this as two separate fractions, the sum of two separate fractions. So we're going to say a over one of our factors plus b over the other factor. Now we don't know what a and b are at this point. That's what we want to try and find, but we are saying that these two expressions, we want them to be mathematically equivalent. And we can say that because we haven't said what the numerators are yet, so we can make them any value to make them add up to whatever the original value would be. So, since it is an equation, let's multiply by the denominator of the original expression, so n times n plus 2. Let's multiply by that on both sides. So if we do that on the left, we're going to be left with 4 equals, if we do that on the right, n times n times n plus 2 times a over n. If we do that, notice that our n's are going to cancel each other out, And we're going to be left with a times n plus 2. And then if we multiply that second fraction b over n plus 2 by n times n plus 2, notice our n plus 2's are going to cancel out, and we're going to be left with b n. And now we can be clever mathematicians, and we can say, since this is supposedly true for all values of n from 1 to infinity, well, that means... Sorry, just kidding. I meant to say that this is true for all values of n, but we're just looking specifically between 1 and infinity. But it should be true for all values of n. Well, except for, values of n that are going to make our denominator 0, which would mess stuff up. But this should work for, say, -2, maybe? Because then if we substitute -2 into this equation, we're going to get -2 plus 2, which is 0. And so we're going to get 0a, which is just 0. So one of our terms is going to cancel, just like the last time, just like in the other problem. So that's going to be our approach. And if we do that, then we're going to be left with 4 equals, if we substitute in -2, our a term is gone, and we're just left with bn, so we're going to have -2b. And so then divide by -2 on both sides, and you'll get b is 4 divided by -2 is -2. And we can do the same thing with a. We can choose a value of a so that our b term goes away, is eliminated. And so, since b times n is one of our terms here, if n is 0, well, then b is going to go away. And so let's do that. Let's make let's make n 0. And if we do that, we get 4 equals n is 0. So we have a times 0 plus 2 is 2, plus b times 0. So it's going to go away. And we just have 4 equals 2a. So a divided by 2 will give you 4 divided by 2. And so a is 2. Cool. So now we can rewrite this, the whole point of this, now that we know a and b, we can rewrite this as the sum from n equals 1 up to infinity of, instead of writing that one single fraction that we started with, we will write this as our value for a, which is 2, over n, plus a value for b, which is -2, so I'm actually going to write that as minus 2 over n plus 2. And you might be looking at yourself and be like, well, who cares? Why am I doing that? That doesn't help me either, because it's still not a geometric series or arithmetic, so I don't have a formula. Well, that's okay. Notice, since we have a negative in front of one of those terms there, we're going to get some negative values, so hopefully some things will cancel out, and that would be awesome. So let's start with our first term, n equals 1, and let's see what we get. 2 over 1 minus 2 over 3. And now let's do for n equals 2. 2 over n will give us, I don't want, yeah, okay, that's fine, plus 2 over 2 minus 2 over 4. And if we do it for n equals 3, we're going to get plus 2 over 3. Notice now we have our first set of opposites, minus 2 over 5. And we can actually stop there now that we have our first repeated value, our first opposite value, because we know that this pattern is going to hold. But let's do a couple more just to be safe. So now let's notice what terms are going to cancel out. Well, look, we've got a positive 2/3 and a negative 2/3. So those are going to cancel each other out. Let's see what else we have. We have a negative 2/4, and we have a positive 2/4. So those are going to cancel each other out. We have a negative 2/5 and a positive 2/5, and those are going to cancel each other out. Now again, recognize your pattern. You're going from one spot, you're going to go 1, 2, 3 spots, and then you cancel. Check it holds. From here we go 1, 2, 3 spots, and we cancel. From here we go 1, 2, 3 spots, and it cancels. From negative 2 6, we're going to go 1, 2, and then that next term is going to have to be positive 2 6, and then they will cancel. That's going to continue forever. So notice all we are left with is 2 over 1 plus 2 over 2. Well, 2 over 1 is 2, and 2 over 2 is 1, so we're just left with a sum of 3. Isn't that cool? Isn't math awesome? Because it's all just about patterns and pattern recognition. Like, for example, there's so many patterns in these numbers alone. Like, look, for example, if you wanted to make writing these terms out easier, look, we've got 1, 2, 3, 4, 5, 6. And if you look here, we've got 3, 4, 5, 6, 7. So you could write this out super, super quickly if you wanted to. Math is the best.